Welcome to this question on circles and trigonometric curves. So it's quite a lot to do here. We're going to scroll down and focus on part A. Here's the curve that we're interested in. Figure 2 shows part of the curve T with equation y equals cos 2x and the circle C1 that touches at these 2 points. So it's also where it crosses the x-axis. I'm just going to write down pi over 4 and 3 pi over 4. We're asked to find the radius of C. So I'm just going to put the center in there as well. To start this then, I'm going to look at the gradient function because that's going to have something to do with it, because you can see they're kind of it's not a tangent, but they have the same gradient at the point where they touch. So that means for t, dy by dx is going to equal minus 2 sine 2x. And then at x equals pi over 4, dy by dx is going to equal minus 2, because it's minus 2 times sine pi over 2. So I can go straight to that. And I could also work out the gradients at 3 pi over 4. And this is going to be minus 2 times sine of 3 pi over 2. And that'll actually be minus 1. So I'll get 2 as my gradient. So I found the gradient at the 2 points. And therefore, if I look at x equals pi over 4 again, the gradient of the normal will equal the negative reciprocal, so it will be a half. Now actually, this is enough information for us to do the question. In fact, we don't even need this bit here. We can see that the center, so let me call the I don't want to call the center, I'll call the center C. You can distinguish from C1. So for the center, x is actually going to be, it's going to be pi over 2, because there's symmetry going on here with the circle and the curve. So it's got to be the midpoint. It's got to be halfway in between. So x equals pi over 2 by symmetry. And then what we've just shown is that the normal, that by the way will go through the center, it must do, it always does. So the normal will go through the center. And we can see we've got this little triangle going on, and we're going along pi over 4 to get from pi over 4 to pi over 2. So we just need to work out what we're going up. But we also know that the normal gradient is a half. So it means if I go along 2, then I go up 1. And that is enough for me to work out this, because it's just going to be a half of whatever is here. It's actually going to be pi over 8. And therefore, the center is pi over 2 pi over 8. And we're sorted now for the radius because I can just subtract the point. Therefore, r squared is going to be the difference in the x's squared plus, I'm using Pythagoras' theorem now on r, so it's going to be this distance squared plus this distance squared. And this one is just pi over 8 minus 0, which I can just leave as pi over 8 all squared. So that will give me, this will be pi over 4, which when I square it will give me pi squared over 16. And then I'm going to be adding pi squared over 64. which will be 4 pi squared over 64 if I times top and bottom by 4. If I then add it, I'll get 5 pi squared over 64. And therefore, r is going to be the square root of 5 times pi over 8. I can just square root each term separately. Now, I've got to say, although I've just gone through this, and I hope it makes sense, the fact that we can use this gradient of a half to get the point pi over 8 really quickly, I didn't actually spot that when I did this question. So I did it a different way. And what I did, and I think a lot of people who did this paper did this, is found the equation of the normal here, and then also found the equation of the normal here, and then looked at where they intersect. So method 2, it's going to be longer, but the equation of the normal through x equals pi over 4 is going to be y minus y1. Now it's just going to be going through 0, so y minus 0, and then that was equal to a half because that was my gradient, x minus pi over 4. I can just get rid of that bit. And then the equation of the normal through the other point, x equals 3 pi over 4, is again going to be y minus 0. I'm using y minus y1 is equal to mx minus x1, by the way. I'm assuming you've seen that before. If not, you can use y equals mx plus c. It's just more complicated. So the gradient here is minus a half. I haven't actually talked about that, but because the gradient here was 2, then the gradient of the normal is going to be minus a half. So I'm not going to write that down. And then it'll be x minus 3 pi over 4. So these will intersect at the center. This is basically a circle theorem. If you have a tangent, then when you have the normal to it, it will go through the center. So what I could do, I can set them equal. So I'll times through by 2 to get rid of that. And I'll get x minus pi over 4 is equal to 3 pi over 4 minus x. That means that 2x will equal pi, and x will equal pi over 2. So that's, if you didn't notice that aspect of the symmetry even, that it's going to be pi over 2, then we've got it here. And now we can get the y value. We can substitute it back into either one, so y will equal a half pi over 2 minus pi over 4, which will equal pi over 8. Okay, and then we're back to being able to find the center like we did here using Pythagoras' theorem. So 2 methods. Obviously, the first one is a lot quicker. But yeah, the second one with the normals is a good method, and it kind of harks back to more, like sort of A-level problems. I remember doing things like that with those kind of questions. On to part B. Well, first of all, we've got this figure 3, which shows again the same curve T, but now a different circle, which touches here at pi over 2 and minus 1. And then for values of x close to pi over 2, the curve T lies inside. So i.e. this is on the outside, the C2 is on the outside. Without doing any calculation, explain why the second derivative for c2 at p is less than that for t at p. Well, remember the second derivative is the gradient of the gradient. So it's how rapidly the gradient itself is changing. And basically the C2 gradient is not changing as quickly. You can see that they both become positive here after they were 0, but t is increasing more quickly. So we just need to write down words along those lines. So I wrote down the gradient dy by dx is changing less rapidly at p for C2 than it is for T. You could maybe just add therefore d2y by dx squared will be smaller or lower. Maybe I should write lower for C2. So I think that's a pretty decent explanation. We're then told that the radius of C2 is r, and we're asked to use the result from B, that the second derivative is going to be less for the circle than for the curve, to find a value of k such that r is greater than k. Now I found this quite challenging, but we can definitely make some headway by investigating the second derivative. So for t, d2y by dx squared is going to equal, now remember it was minus 2 cos 2x. No, sorry, minus 2 sine 2x was the dy by dx. And so I'm going to get minus 4 cos 2x. And I could even look at what happens. Remember, this point here was, let's just not forget, it was pi over 2 minus 1. So at x equals pi over 2, d2y by dx squared will equal 4, because cos of pi is minus 1, so it's minus 4 times minus 1. Now, that leaves us with the circle. We've got the circle, it's going to be coming around, and it's going to have center, say, here. Again, by symmetry, it's got to be when x is pi over 2. But what about the radius? Well, well, we got the radius which we're trying to find, but also the y coordinate of the center. Now this distance here is r. So if I want to work out this coordinate, well, okay, remember this was minus 1, and therefore the center is going to be minus 1 plus r, or r minus 1. And that's the trick to this question. You've got to realize you can't just be working in terms of A and B. We're trying to use R, and so we need to write it in terms of R, because that allows us to write down the equation. X minus A all squared plus y minus B all squared will equal the radius squared. I hope I've convinced you about that, because I think this is the trickiest bit to get your head around. Now we want the second derivative of this, so we're going to need to do some implicit differentiation. I'm going to differentiate with respect to x, and that will give me 2x minus pi over 2. I'm also just gonna, I'm not gonna write a whole other line, but I'm gonna change this to, it's gonna be minus r, but then it's gonna be plus 1 when I take the negative. So when I differentiate this, essentially I differentiate it with respect to y, so it'll be 2y minus r plus 1, but I need to differentiate the inside with respect to x, and that will give me a dy by dx, and that's going to equal 0. There's a common factor of 2, so I can cancel that. Now it might be tempting to make dy by dx the subject and differentiate it again, but you'll end up using the quotient rule. It's going to be messy. So here's a hint. Don't do that. Just differentiate again, and we're just going to have to, you know, although I will, okay, to be fair, we should get dy by dx by itself. So it will be minus x minus pi over 2. We're going to need to use that, but don't, you can, but I wouldn't advise differentiating this because you end up having to square the bottom and all that sort of stuff. So instead, differentiate again. Differentiate with respect to x again. Are you ready? Let's do this. So we're just going to get 1 from differentiating this term. And then I'm going to need to use the product rule on this because they're both functions of x, remember? So I'm going to get y minus r plus 1, and then I'm going to differentiate again to give me d2y by dx squared. Remember, that's the thing I want. And then if I differentiate this term here, I'm just going to be left with dy by dx. So it's going to be dy by dx times dy by dx, which is dy by dx squared. And that's what I was talking about when I said, actually, it will be useful to make this a subject because I knew this was going to happen. And now we can substitute in for it. So I'm just not going to rush it. 1 plus y minus r plus 1 d2y by dx squared plus this thing squared. I can just get rid of the negative. And just put a whole squared around it, and that's going to equal 0. And we can now rearrange this to make d2y by dx squared the subject. So I can minus 1 from both sides, minus this thing all squared. And then divide through by y minus r plus 1. I've got to square it. So I could potentially tidy this up, but I'm not too worried. And what I'm interested about is at pi over 2 minus 1, what the second derivative is. So that'll give me minus 1. And actually this term, this is brilliant. I just get 0 here. So it's going to be minus 1 over minus 1 minus r plus 1, which is just going to be 1 over r. So suddenly this has become really nice. That's the second derivative. And remember, we have this second derivative for t is 4. And we have the second derivative of the circle is 1 over r. So using b, it must be that 1 over r is less than 4. And to solve this, you can kind of times through by r divided through by 4, but you have to remember to switch the inequality sign around when you deal with reciprocals. It's actually going to be that r is greater than a quarter. And hopefully you can sort of see that if r is equal to a quarter, then obviously they're the same. Let's say that r was equal to 1 over 8, then you'd get 8 here, which is not less than 4. So whereas if you put in a half, for example, you'd get 2. So I hope I've convinced you that you do need to switch the sign. I'm just going to tidy up that. But there we go. That is what the question was looking for. That is by far the hardest part of this question, I think, doing all of this. The final part is actually not so bad. Back up to here. Given that C2 cuts T at the point 0, 1, that's here, find the value of R. So remember, we have the equation of our circle, x minus pi over 2 squared plus y minus r plus 1 squared is equal to r squared. And now we have a point that it goes through. So the only unknown will be r. So at 0, 1, we're going to get, it's going to be 0 minus pi over 2 all squared. So we'll get pi squared over 4 plus, when I put in 1, I'm going to get 2 minus r squared. That's going to equal r squared. So I'll get r squared minus 4r plus 4 equals r squared. These can cancel. So I'll have 4r is equal to 4 plus pi squared over 4. And therefore r will equal 1 plus pi squared over 16. I could alternatively put it all over common denominator, couldn't I? 16 plus pi squared over 16. Okay, nice job.